Hello, this is Titus Dudden. I'm here for Project 5 of CpE 3110. For the first circuit of the project, we are doing a simple computer state machine that has no external inputs other than a start and a reset that I threw in there. This is pretty much a proof of concept circuit, just showing the next state logic through fetch, defer, and execute, and then the output logic showing the fetch signal, the defer signal, and then the execute signal. This is a circuit that is kind of bare bones and will be used for the second circuit in this project. Going over to hardware testing, if we throw a start high, I do have this hooked up to a clock. You can see that it runs through the 3 states and then or the 4 states, and it'll bump up to defer, then bump to execute, then it'll fall back to fetch. And it will repeat this cycle until the start is dropped and the reset is thrown high. And again, this is just a simple cycling circuit, so it's nothing too crazy there. Moving over to Cordis, we can see what the block looks like. Or well, I guess I'll show off the RTL first. This is the state logic blocks that we have here, and then these are the 2 control inputs. These are going to be registers over here that are for all of our control signals that are being shown off from all of the state signaling. Moving over to the block as well. I'm doing this a little out of order. We can see that I ran a big counter to slow down the clock so that we could actually see everything. And then I just ran 2 input switches and then everything to output LEDs. So once again, just to show it, because this video feels shorter than it should be, we can see it cycling through. And that's going to be everything for the circuit. Okay, this is the second circuit of Project 5. What this is, as previously stated, the previous piece of code was bare bones. This I'm doing things with. So we have a start, a clear, a reset, all of the states, the state, the next state, opcode, and then all of our control signals as outputs. These are all internally registered. I just have them organized so I can see better. Then the symbolic names for states, the assignments for all of the control signals, the state register, the next state logic, which this is, since I'm doing direct, what it is the 0th bit of my opcode is going to be a 0. So I'm not actually doing any kind of, I won't be doing defer states. And of course, this is all hypothetical, so we're assuming that the clock cycle that the tasks are being done in can be completed in that clock cycle. So there should be effectively no defer states for this. Moving on to the output logic, we have all of our default states all just ran to 0s. And then the fetch case is the same for all versions of opcodes. So it's just all of the control signals that correspond to fetch. And the same thing for defer, all of the control signals that correspond to defer, which I'm not going to spend a bunch of time going into what every single one is. I'll do that during the hardware test. And then the execute is where it becomes opcode specific, where we have both opcodes, a third opcode. Moving on to the next one, we have both opcodes, the third opcode. And then for the third one, all of them are doing something different. And then for the last one, all of them are once again doing something different. And this is more of a proof of concept than anything, because unfortunately, due to time constraints, I'm not actually moving any data, which was not the original task, but the original task was to have it read from memory. But I won't be doing that due to time constraints. I will simply be getting this project done. And then this is what the block diagram looks like. I ran every single pin that I'm not using to ground so that I can tell what is on and what isn't on. Moving over to the RTL, it is the same as the previous circuit, except much larger. because rather than having 2 or 3 control signals going to outputs, we have way more control signals going to outputs. And some of them are both dependent on selector muxes and the states that it resides within. And I'm going to move over to hardware testing now. So for this setup, I've got it sideways because I have all of my labelings. So I'm gonna throw this start high, and then we will move forward. As you can see, we're gonna be doing a little bit of back and forth here if I can figure it out. As you can see, it's PC bus 1, TRA1, bus 3 MAR, MAR to MBR, and that is everything that is showing up in this first one. Move to the next one. It is incrementing the PC counter. Then moving forward, it is loading the index, and then the next one, it is loading the the index to bus, and then bus to MAR. And then as you can see, the state, it will go from fetch straight to execute. And let's make sure I have my opcode set correctly. I believe it's this. Let me double check super fast. Because I'll go ahead and do mul since it's the most complicated setup that I have here. Which should be 00111 and the extension bit, and then the indirect flag. And then I will take it down the line. So MAR to MBR, and then it will load the MBR to bus 2, the accumulator to bus 1. The upper bits of the accumulator will go to, the bus 3, the upper bits will go from bus 3 to the accumulator. The lower bits of the result will go from bus 3 to the lower bit, and you can see our multiplication flag is also high. And then for the next state, it waits to move on back to state 1, or the fetch state, and then it jumps back to fetch. And I can go ahead and show off another one since the first video was fairly short. I will do store. So once again, the fetch states are all the same, and we wait for it to jump to execute. So now it's in execute. So the accumulator loads to the MBR, and then the MBR loads to the MAR, and then it waits, and then it does nothing for its final state, which is it moving back. And since that one went fairly quickly, I'm kind of just doing it out of order here now. I'll go ahead and do LDA. So once again, fetch is all the same. And now that we're in execute, it loads the MAR to the MBR, and then it waits, and then it runs the MBR to bus 2, and then it does TRA2, which then takes the MBR to bus 3, and then bus 3 loads it to the accumulator, and then it waits, and then it goes back to the fetch state. And that is a very long-winded explanation of this final circuit.